All right, hello again. Welcome to the third lecture. Okay, we'll pick up where we left off with the main geometric formula for the square of the Witten-Dirac operator. This Dirac operator that we make on the SL2C spinor bundle using the connection from the Lorentzian manifold N. Okay, this is the heart of the argument. This type of formula is called a Weissenbach or Lishnarovich or Bachner type formula, where you square a Dirac operator and compare it to its rough Laplacian. Okay, so let us begin. This is a good skill to have to be able to compute formulas like this. So let's see how it works here. The actual formula is pretty complicated, relatively speaking. It's here, as I've recorded in this proposition. And so on the left-hand side, we have our Dirac operator twice. Here we have a rough Laplacian, which by that star, I mean the adjoint of connection with respect to the, nabla bar, with respect to the inner product on our manifold. But concretely, it's just minus the sum of the squares of nabla bar I on the spinor, I going from 1 to 3, where that's the orthonormal basis for Tm. Okay, so that's the expected stuff. And then you have the curvature term, which is the interesting one here. Okay, it will be controlled by the dominant energy condition, but geometrically speaking, it's this. 1/4 times the scalar curvature of the Lorentzian manifold, plus these two things, Ricci curvature in the 0, 0 direction, so the time direction off of the slice into n, and then plus some portion of the Ricci tensor, mixed terms. Here, j is ranging from 1 to 3, just the space directions. And then you have this 2 Clifford multiplication acting on psi. So these are just numbers acting by scaling, and this term, you have to do a little bit of Clifford multiplication. Okay, good. And then there is a term coming from the second fundamental form, Kij, with some Clifford multiplication times, acting on the derivative of psi. Okay, good. So let's so to establish this formula, which is the main thing we'd like to do in this lecture, let's choose a basis, which I've been talking about implicitly. You have, so here's the little picture, M inside of N. Here the EIs are tangential, E0 is normal and of length -1. And let's choose for ease of this type of calculation, let's choose the tangential basis so the Christoffel symbols vanish in these in this frame. For instance, geodesic normal coordinates for the Riemannian structure on M. Okay. Good. Let's notice a few things before we jump right into the calculation. So by definition, I didn't mention this earlier, but this is the definition of second fundamental form. It is what you get when you take the Kij, the second fundamental form on EI, EJ. It's just the normal part of the ambient connection, taking the derivative of EJ in the EI direction. It's just the normal part of that. In these coordinates, the tangential part of that vanishes, so there's only a normal part of it. So this is all there is when you take this kind of covariant derivative. Okay, or if you wanted to write down what EIEJ is, that would be minus Kij E0. Okay, you just pair both sides with E0, you get the above formula, since E0 with E0, the pairing of E0 and E0 is -1. Okay, well, we'll use that in a second. All right, so now let's start the calculation. We're trying to establish this proposition, this Weizenbach-Bachner type formula. Let's go for it. Okay, so let's just write down from definition. What is Dirac twice? Well, one Dirac is in this frame. You just do EI multiplying Abel-Bar EI, and then you are applying that to the Dirac operator, which is the sum over J of EJ and Abel-Bar J, all acting on sign. Okay, the first few steps are going to be very familiar. Okay, so this use the product rule here to break up this first covariant, this outer covariant derivative. Okay, you get two terms. Nothing funny going on here. Okay, this first term we can express in terms of the second fundamental form, and we will do so just by the above observation. Okay, and that completely takes care of this term. This is, this is what appears in the formula. Okay, so that takes care of that term. That's where that appears. And then let us break up this term where I'm summing over I and j equal to going from 1 to 3 into two different terms. I'll first consider the term you get when you sum over I equal to j. So this is the I equal to j part of this double sum. And then down here, this is the I not equal to j part of that sum. Now, as I've indicated over here, when I is equal to j, so this, sorry, there's a little typo there. This should be an I. Well, EI acting on EI, acting on a spinor is the same as acting by -1. Since EI is tangential and EI squared is -1, Clifford multiplication. So this is exactly the term, this is the rough Laplacian term, this term here. Because if you pick up a minus sign from this Clifford multiplication, that is exactly that. Okay, so we've taken care of two terms, and we're interested in, so the remainder of the proof will be devoted to understanding this remaining term, which is where all the interesting stuff happens. The other two parts are, that'll basically happen in any type of formula like this. And the hard work is to establish what is this term in a geometric sense. Okay, so let's do some work. First observation. Notice that if you swap okay, you got the fix I and j, you got a term in here. If you swap I and j and then add those two terms together, so you got an I is equal to 1, j is equal to 2 term here, and you also have a I is equal to 2, j is equal to 1 term here. Let's add those together and notice that, well, you can get the same coefficient of the Clifford multiplication, guys, by just swapping the I and the j, swapping this multiplication, picking up a minus sign. So when you do that, when you add those two things together, you can get a common factor of EI, EJ acting on a difference of covariant derivatives. Second covariant derivatives here. Okay. Good. So if I want to write this, okay, so really I can just write this as a sum over just I less than j of these things, because I can take the two swaps of each other and combine that into a single term given by what I'm boxing right here. Or since what I'm boxing here is symmetric in I and j, I can just sum over all of I and j, and but then I'm adding up things twice. So I'll put a 1/2 here. So this term summing I not equal to j is the same as summing over all I and j of this business, EI, EJ, and then the difference of these two second covariant derivatives. And you can also throw in the I equal to j terms, because that's obviously going to vanish here, because the covariant derivatives just be the same, they cancel each other out. So adding in the I equals j is harmless, but then adding over not only I less than j, but I bigger than j, you have to pick up a factor of a half if you want to do that move. Okay, anyways, there's nothing fancy going on here. However, this is the problem, or this is the where things get a little bit more interesting. Well, this definitely looks like something to do with curvature. Nabla bar I, the commutator of the covariant derivative, that involves curvature. That is curvature. But this is curvature acting on a spinor, which we want to reinterpret, or we want to recognize as the usual curvature that we know about, which is, differentiating vector fields, not differentiating spinors. We define our notion of sectional curvatures and scalar curvatures using vectors. So we want to relate this to how the covariant derivative acts on vectors or covectors. Okay, yeah. So for instance, usually you would call this the Riemann curvature of the pseudo-Riemannian manifold N. I'll put a bar for it being from N. IJKL is what you get when you do the commutator covariant derivative in IJ acting on EK, and then you take the Lth part of that using the metric H. Okay, and, this is a number like we're used to, perhaps. Okay, now maybe you know this, maybe not, but once you have calculated all of these numbers for all combinations I, J, K, and L for your given on your given manifold with your given connection, you can organize all of that information, all those numbers, into many different forms. You can think of it as a 4 tensor like this, but you can also organize it into algebraic object as an endomorphism of the second exterior power of the tangent bundle, or cotangent bundle, or whatever you would like. You can go kind of either which way. Okay, and here's how it works. So we'll write that as R bar still. So R bar is meant to be this endomorphism I'm talking about, the way of viewing the curvature tensor. And you define it in the following way. Well, you want to say, okay, what kind of form does R bar of EI wedge EJ give me? Well, I will tell you the EL wedge EKth part of it. And that is the number that we're used to, the R IJKL. Notice the reversal of the LK. Okay. In order for this to have the right symmetries, you need to do that. Good. So you can view this as a endomorphism, or you can view curvature as an endomorphism of lambda 2. You can also view, an endomorphism, a map from a vector space to itself as an element of lambda 2 dual tensor lambda 2. So you can say how just plugging in a single 2 form into this endomorphism, how that acts on something in lambda 2. And so you would say that this acts by the following, pairing with the following one form, or pairing, I've written the dual basis here, so that's like something that eats in 2 vectors. So it acts like this: RIJKL, and then DXL wedge DXK, again with the K and L reversed. Okay, so we can make sense of how. So this object here is how Nabla bar I nabla bar j minus nabla bar j nabla bar I acts on lambda 2 Tn. So if I wanted to write down a formula, if I wanted to say, okay, this thing acting on some 2 form alpha, I would write down this thing acting on alpha, where we're interpreting this as a function on two forms, or pairing with the dual element of lambda 2. All right. So we know how it acts on lambda 2. We would like to understand how this acts on the spinors, the representation that we're interested in. All right, so let me let us review another few basic things. So the Lie algebra of SO31 can be identified with a second exterior power of the underlying vector space. In general, you can do that. A special orthogonal group of a vector space with an inner product can be identified with lambda 2. What is the map, roughly speaking? It's the following. You take EI wedge EJ and you send that to the infinitesimal generator of rotation in the EI EJ plane from EI to EJ. Okay, good, that's on one hand. Now on the other hand, remember we have a map from SL2C to SL plus 3,1. That's spin 3,1, that's the double cover map. So the Lie algebras of these two things they're definitely isomorphic. Just to be clear about what I mean by Lie algebra, the Lie algebra is just the tangent space at the identity of the Lie group. That's what I mean by Lie algebra. That's what these objects are. These are the Lie algebras, tangent space at the identity. Okay, since these are since it's a covering map, local diffeomorphism, the tangent spaces you can definitely identify them in very strong sense. Whatever, if we want to keep track of this isomorphism, this is a 2-to-1 map, and roughly speaking, the differential has something to do with there's a times 2 involved because it's 2-to-1 nature. And if you want to reverse that, instead of going from up top to down below, we want to go the other way because we know how things are going on over here, over in lambda 2 land. We want to know how to interpret them over in SL2C land. We have to divide by a half. Okay, and now SL2C acts on S because so the group acts on S, and when you're in that situation, then you have a canonical action of the Lie algebra by basically taking a derivative of that action. In this case, it's the adjoint action. It basically acts by Clifford multiplication, EI, EJ. Okay, so if we want to follow, how does this work? How does something over here act on something over here? Let's call that action rho. Rho of a 2-form, EI wedge EJ, is a half Clifford multiplication by EI EJ. Or you could say it, sometimes people say it's a quarter Clifford multiplication by the bracket EI EJ. It's the same thing. Okay, so continuing on, here we go. We wanted to understand this term, the action of this piece of the curvature endomorphism acting on a spinor. Well, it is Rijkl, Rijlk rho dxk wedge dxl acting on psi, which if you want to reverse the L and the K to write them in the usual order, IJKL, you pick up a minus sign. Then we also get a half from this rho. Okay, so let's go back to what we were doing. By the way, these things here, I didn't mention it, but they're going from 0 to 3. They're going from 0 to 3 because we are looking at the curvature of n. All this discussion was the curvature of n. So when we want to write the portion of the curvature, in here, it's this big sum, but where we have to sum over everything from going from all 4 of the variables. All right, so now we're okay. That was our side discussion. We're trying to understand our desired, interesting curvature term. Okay, so here we are. So we're here, and we have just used our new formula that we just learned about for how curvature acts on the spinors. We just put that in at the cost of a minus sign, and we picked up this extra 1/2. Okay, and that was a 1/2 from before. So here's the setup here. It's a little bit confusing because half of the sum only goes from 1 to 3, and another half goes from 0 to 3. We got to keep track of that. I'll keep track of that in the red letters. Those will go from 0 to 3, and then we'll adjust later when there's not much confusion anymore. Okay. Good. So now the first step, I'll, here, the sum is symmetric in K and L. The curvature, the Riemann curvature is antisymmetric in these 2 entries, and Clifford multiplication is antisymmetric in the K and the L. So I'll just change this from a K less than L to a range over all K and L just by adding another factor of 1/2. So now we're up to 3 factors of 1/2. We have a minus sign. K and L go from 0 to 3. I, J go from 1 to 3. All right, so now let's write the whole thing. Let's go, I and J go from 0 to 3. Okay, so let's throw in those extra terms that we're missing. Yeah. Okay, so now we get the whole thing. Everything's ranging over every possible thing in our sum. And then what is left over? We have to subtract off some stuff. Let me zoom out here so you can see everything. And zoom up so you can see everything. Okay, so what do we have to take off? So what was this missing? It was missing the terms you get when I and J were 0. So for instance, if one of them is 0, then I want all the other 3 things to range over all numbers. All of those terms were missing from before, from the line up here. So we have to add all of these. And you have to do the same for both I and J. So this term is missing, but also R, little r, 0, K, L, ... was missing. But this whole term is symmetric in I and J, so I will just combine them into a single term and add a 2 there. Okay, so those are like the 2 things in this sum that were missing, and we subtracted them off, and now we have equality. These 2 things are equal to each other. All right. Now let's take a look at the big one. This one will be the easier to interpret, and then we'll see how to deal with the other one. All right. So here we are in the big sum, ranging over everything. I'll stop using red because now we understand everything's ranging over 0 to 3. All right, so I'll take the EL out and then have the sum. I'll do the EL at the very end. Let's look at what's going on the inside. Let's break up the sum on the inside, where we're just summing over I, J, and K, into 3 different pieces. Let's range over the terms where they're distinct, where I, J, and K are not equal to each other. Then the terms where, I'll write this in the red here. These are the terms where K is equal to I, And then these will be the things in the triple sum where k is equal to j. Okay, and then every term in the triple sum lands in one of those categories. Yeah. Good. Yeah. All right. So yeah, that's right. Okay, so now let's analyze each of these. Okay, so why did I do that? What was the whole point? I want to use the Bianchi identity. The Bianchi identity will tell me that this first term vanishes. Okay, so that one goes to 0 by Bianchi. Good. That's exactly why I pulled that out. Now, let's analyze these other two terms. They are actually the same. If you notice, they don't look that different. By canceling canceling out these things. Okay, so if you just switch the I and the J, you pick up a copy of -1, and then you combine EI times EI, that's just a +1, more or less. And similar here, you do a swap, or you don't have to swap at all, you just pick up a -1. Except there's a little caveat, which is when J is 0 or when I is 0 up here, then EI, E0 is +1 instead of -1. But that won't affect the overall outcome of the calculation. That's the side. So they're not always equal to these, but heuristically. Okay, yeah. And then if you use the antisymmetry properties, this -1 will go away. Okay, so we have two copies of the same term here, summing over all, and I'll throw back the L now. So we have sum over L and the sum over I and J of this business. Okay, notice this is, if we sum over the first, okay, if we just sum over the I first, then this is like summing over the first and third entries. That's the Ricci curvature. Again, there's a little bit of funny business going on here by that E0 is 1 and EI is -1, but let's ignore that for now. All right, so we're here. We recognize that as Ricci curvature. Well, Ricci curvature, it's symmetric in J and L, and it's antisymmetric in, in this Clifford multiplication is antisymmetric. So all the terms where the J and L are not equal to each other will vanish. And so we only get when they're equal to each other. And again, this is like a +2 Ricci 0, 0. This should just go from 1 to 3. By that same thing I mentioned before. And so when you add up all these things, you get -2 copies of the scalar curvature of H. Okay, so that was what was going on with this first term. Now let's do the same maneuver on the second term. Applying the same idea, you can identify that second term with this amalgamation of the Ricci tensor in the 0J direction and plus Ricci in the normal direction. And this should be summing over J. Sorry about that. Okay, which establishes the final formula. That's what we were interested in establishing, which we've got here. notice that we had a 1/8 out in front of all of this term, and then we had a 2 in front of our h, and then we have a 4 in front of this business. So, you pull out a 2, you recover this, and then it's twice that. Okay, very good. So that is this Lishnarovich formula for the Witten Laplacian. Okay, that'll be it for this lecture.